Okay, let's prove the missing direction from 3 to 1. So we assume this, and we want to show that the function f is convex on C. This means that we want to compare f of 1 minus lambda x plus lambda y with f of x and with f of y. To this end, as we have seen from convexity to this expression with the gradient, we had to do some limit of difference quotients. So we had basically formed the derivative. And now we have to integrate in order to get back to convexity. So let's see how we do this. We can take the function, I think. So we can actually take f of x plus t y minus x. Okay, what do we do? Since f is differentiable, we can take the derivative with respect to t, and then we integrate this with respect to t. And like this, we get f of x plus t y minus x. Okay? So let x and y be in C. Let lambda be between 0 and 1. What we can now do is, since we want to compare the convex combination with t equal to lambda with the point f of x with t equal to 0, I think I missed a parenthesis here, we can just integrate this thing here from t equal 0 to t equal lambda. What do we get then? Well, this is just the integration over some derivative with respect to t. So we get f of the upper limit, x plus lambda y minus x, and minus f of x when we set t equal to the lower limit here. So this is this integral here. Okay, so now we know the chain rule, so we can actually write this derivative here in a different way. Namely, we can take the gradient of f at this point and take this in the inner product with the inner derivative here with respect to t. So this is y minus x. And this is this d by dt of f of something something. Okay. So now we want to use point 3 here. And we see that we have a gradient in the inner product with something. And we want to replace this with some other gradient in the inner product with respect to the same thing. So we can replace gradient f of something by gradient f of some other thing under some circumstances. This is what number 3 says. And I claim that we can replace this by the integral from 0 to t over gradient f of x plus lambda y minus x. Y minus x. Why is that? We have gradient f. So here we have something greater or equal than 0. So let's start here. Gradient f of x plus lambda y minus x. y minus x, and this y minus x is actually in both of these things. So let's get rid of write first. Yeah, let's first subtract this thing here, the other gradient. Okay. So minus gradient f of x plus t y minus x. Okay. And here we have the difference of gradients at some points. So this axis is in common. Then we have lambda y minus x and t y minus x. And if we write lambda minus t y minus x, then we see that I screwed up. So the upper limit is of course lambda as in the very first equation, the very first integral. So t is between 0 and lambda. So lambda minus t is always greater or equal than 0. So we can pull this out. And we have that this expression is 0 by 0.3. Okay, so because this is always greater or equal than 0, we can pull this out, and then we get this thing minus this thing. So the lower expression, the lower expression below minus the expression above, scaled with this non-negative factor, is greater or equal than 0, and therefore this inequality here holds. Okay, this was a bit complicated, and now we have shown this, and we see here that there is no t left, so we can actually multiply this with lambda. And now we have gradient f of x plus lambda y minus x, y minus x. Okay, so we have shown this is less or equal than this. And analogously, we can do this for lambda to 1. And for lambda to 1, we also want to estimate this. We will also estimate this so that we get this gradient f at this point in the middle. And this is most easily done by just changing x and interchanging x and y, and lambda and 1 minus lambda, so that you get y plus 1 minus lambda x minus y, which is actually the same expression. So change x with y and lambda with 1 minus lambda. Okay, I don't want to waste my space here. So then we get f of the same expression minus f of y less or equal than 1 minus lambda gradient f, again same expression, and here we have to change x and y. Okay, so we have this, and now we multiply this first thing with 1 minus lambda and the second thing with lambda. So multiply the first inequality with 1 minus lambda, then we have lambda times 1 minus lambda times this gradient at this point times y minus x. And here we have, if we multiply the second equation with lambda, we also have lambda times 1 minus lambda gradient at this point in the middle. And then we have x minus y instead of y minus x. And therefore, these things cancel out. So multiply the first inequality with 1 minus lambda, the second with lambda. And then we, in fact, get what we want. So we get lambda times this, 1 minus lambda times this, plus lambda times this, perfect, is 1 times this, so x plus lambda y minus x, minus 1 minus lambda f of x, okay, minus lambda f of y, and then this thing is less or equal than 0. And this proves the convexity of f on C, because x plus lambda y minus x is 1 minus lambda x plus lambda y. 1 minus lambda x plus lambda y. And this is exactly the convexity. Okay, so now we have shown the theorem for once differentiable functions, where we only have gradients. So let's now move on to the next theorem. So theorem, again, let C be a subset of H, such that C is convex and open, and let F from C to R, again differentiability, so no plus or minus infinity, be twice differentiable. Then F is convex if and only if gradient of, not gradient, the Hessian of f at the point x is positive semidefinite for all x in C. All right, proof. For this theorem, we can, of course, use the properties we have for once differentiable functions, which we will actually do. So first proof, so the first direction, we have to show two different directions. First direction, let f be convex. What do we have then? Well, the Hessian is the second derivative, so it's the derivative of the first derivative, so the derivative of the gradient. How can we express this? Let D be in Rn. Then we have the Hessian. The Hessian, this is an operator from the gradient. The Hessian at the point x is an operator, a linear operator from h to h. So we can apply this to a vector d, and we have to show that this Hessian is positive semidefinite. So if we take the inner product of d with the result of applying the Hessian to d, then we should always get some non-negative number. That's our goal to show. So what can we say about this expression? As I've mentioned, this is the second derivative of the Hessian, and therefore we can write this as a difference quotient of this is the derivative, the first derivative of the gradient, and therefore we can write this as a difference quotient of the gradient, namely as gradient f of x plus td minus gradient f of x divided by t. Okay? Okay, now we have to take the inner product of d with gradient f of x applied to d. This is this thing in the inner product with d. The inner product is a continuous mapping so that we can pull out the limit. So we can write limit t to 0. And we can write gradient f of x plus td minus gradient f of x. And now we have d. We have the d here. I switched the order. Probably not good. So we have x plus td minus x. We have d, and then we have this is td. So we have to divide by another t, and we have to divide by this t also. So this has to be here. So we divide by t squared. So this is the limit of 1 over t squared of this thing. And now we see here gradient of something minus gradient of a different thing, some different thing in the inner product with something minus the different thing. And this is again our monotonicity property, which shows us that this is greater or equal than 0. So this is actually greater or equal than limit of t to 0. Limit t to 0 of 1 over t squared of something which is greater than 0. So this is greater than 0 by property 3 of the previous theorem. And we're done. So we took this property here. We showed that for this difference quotient here, we can apply this to show that d in the inner product with gradient squared f of xt is always greater than 0. By the way, that c is open, which is written here, is important because otherwise, if we're at the boundary, we can't take this limit of x plus td. So since the set C is open, we can go some small step in every direction. So we can actually take t small enough such that for any d, f of or x plus td is still in the set C. Therefore, open is the property that C is open is important. So in C for t small enough, that's important. Okay. This is because C is open. Now we have to show the other direction. So let this Hessian nabla squared f of x be positive semidefinite for all x in C. And we want to show that f is convex. How can we do this? We apply Taylor's theorem. And Taylor's theorem says that for all x and y in the set C, we can write f of y as f of x plus gradient f of x y minus x. This is the first order Taylor approximation. And then we have the remainder term, which contains almost the same, except that we don't take the Hessian at x as we did here, but we take the Hessian at some point psi in between x and y. Okay? Okay. With psi, this is some point in between, so this is 1 minus lambda x plus lambda y for some lambda between 0 and 1. Actually, for Taylor's theorem says that it is actually in between, and it's not exactly 0 and it's not exactly 1. So it can always be chosen in between. So this is in between. So we are using the positive semi-definiteness of the Hessian at the point psi, which is in between here, to show that f of y, since this expression here is greater or equal than 0 by positive semi-definiteness, so that this is greater or equal than f of x plus gradient f of x y minus x plus 0. And this is exactly property 2 here. So by property 2 of the previous theorem, we know that f is convex. And this concludes our proof.